Okay, so section 5.2 deals with diagonalization. So before we can discuss what diagonalization means, we need to first look at what a similarity transformation looks like. Okay, so if P is an invertible matrix, and we multiply a square matrix A on the left with the inverse of P and on the right with P, that is called a similarity transformation of the matrix A. Okay, so if A and B are square matrices, then we say that B is similar to A if we can find an invertible matrix P such that we can express B as P inverse AP. Right, now in this particular example here they give the matrix A and the matrix B, and they just illustrate that B is similar to A because I can find a matrix P such that P inverse AP is in fact the matrix B. Okay, so the next page, we look at some interesting properties of this similarity transformation. So if B is similar to A, in other words, we can find a matrix P such that B is P inverse AP. If we can find such a matrix, right, then under this invariance transformation, there are some properties of A that stay the same after we've applied this operation to get B. In other words, B will have the same properties as A. For specific types of properties which we are going to look at now. And the first property is that the determinant of A is going to be equal to the determinant of B. Right, now to see this, again, that's straightforward because I just use the property of the fact that the determinant distributes over a product of matrices, right? So that's going to be the right. So again, the determinant distributes over the product. So that's going to be the determinant of P's inverse multiplied by the determinant of A, right, multiplied by the determinant of the matrix P. Okay, and again, those are all real numbers. So we're left with the determinant of P multiplied by the determinant of A multiplied by the determinant of P. Right, and therefore that becomes the determinant of A. Alright, so that's one property that's invariant under this similarity transformation. Right, the next one is, again, if you use a similarity transformation, you don't affect the invertibility of A. So if the only way A can be invertible is if after the similarity transformation, the matrix that we get, which is B, is also invertible and vice versa, right? So why is this the case? Right, so let's assume A is invertible. Right, so under assumption, we can find a matrix C such that A times C is the identity matrix. Right, now because B is P inverse AP, we have that A is PB P inverse. And so replacing A in that term there, we obtain the equality. And from that, it follows that. Right, so multiplying on both sides on the left-hand side with P's inverse. So you multiply there with P's inverse. You multiply there with P's inverse. Okay, we obtain the next expression. Right, and from that we obtain then that P inverse CP is equal to the identity matrix. Right, so it follows that B is invertible, and B is invertible because this is B's inverse. Right, so also note that if we take this term here and we multiply on the left-hand side and we multiply on the right-hand side with P's inverse, then we get obviously this term here, and C is A's inverse, so therefore we can place CA with the identity matrix, and therefore right, so that term there is equal to that term there, and therefore you multiply with a P there and with a P there, and that will become the identity on the right hand side, and therefore multiplying B on the left hand side with that term is also the identity. Okay, but you didn't have to check this note because there's a theorem that states that you only have to check the you only need to check the right hand side or the left hand side. One is enough. Right, so so invertibility doesn't change. If you use an invariant transformation on an invertible matrix, it is invertible. Right. Now we can now for this if and only if we can assume that B is invertible, and by the same argument you can prove that A is invertible. Right, so that invertibility is never going to change. Right, so property 3 and 4 states that under this similarity transformation the rank doesn't change and the nullity doesn't change. So what is the rank again? It's the dimension of the row space. And the nullity is the dimension of the null space of A. So when you do this invariant transformation on A to get B, the new matrix is still going to have the same rank, and the new matrix is still going to have the same it's going to have the same nullity. Okay, so I just quickly want to look at property 4. Right, so let's take a basis for the null space of A. Right, so there's the basis, and we're going to use that basis to find a basis for the null space of the matrix B. Right, so recall that AP is the same as PB. Right, so let's take a vector y to be in the null space of B. Then if you multiply on both sides with the vector y, you get equality, and that's going to imply that that A times Py, that whole vector there, that's going to be 0. That's going to be the 0 vector. And why is that? That is because y bar is in the null space of B. So multiplying it with the matrix B is going to be the 0 vector. And the 0 vector times P is the 0 vector. Okay? Right, so therefore the matrix Py will be in the null space of the matrix A, because multiplying it with A gives the 0 vector. Now because Py is in the null space of A, we can represent Py as a linear combination of the vectors in this set here. Right, so there's my linear combination. Remember, the V's are the V's form a basis for the null space of A. So therefore, I can express that Py bar as that linear combination. So because P is invertible, we can then go and solve for the vector Y. So hence, right, so basically we've just proved that Y is basically in the span of this set of vectors, right? P inverse V1. So we've basically almost formed a basis for the null space of the matrix B. Right, so all we need to do to show that to find a basis is we just need to make sure that these vectors are linearly independent. Just for argument's sake, take those vectors there. Let's set up our linear independence equation, and from that we then have, okay, and then multiplying through by the matrix P, we cancel that out pretty much, okay, and we are left with this whole equation. And because the V's are linearly independent, it means all these K's are going to be 0. All right, so that's a linearly independent set. Okay. Right, so therefore, this whole set here is linearly independent, and it spans the null space of the matrix B. So therefore, that is a basis. So what is the dimension of the null space of B? The dimension of the null space of B is M. And what is the dimension of the null space of A? It's M. It's the same, right? So it follows that the nullity of A is the same as the nullity of B. I recall that the rank of A plus the nullity of A is N, and the rank of B plus the nullity of B is also equal to N. Right, from that it follows that N minus the rank of A is equal to N minus the rank of B. And remember, we said that the nullity of A is equal to the nullity of B, so we can equate those two expressions, and so therefore follows that the rank of A is equal to the rank of B. Right, so this invariant transformation, or this similarity transformation, doesn't affect the rank and the nullity of a matrix. Right, so the new matrix is going to inherit the rank of the old matrix. Right, so it seems that the trace property is also not affected by this similarity transformation. Right, so if we look at the trace of A, we can replace A with P, B, P inverse. And just recall that the following holds. If you take the trace of A times B, that is the same as the trace of B times A. Remember that? Okay. Okay, so applying that rule, we take that matrix there, and we take that matrix there, we switch the two around, and we take the trace of that. Okay, and therefore that becomes the trace of the matrix B. Okay, so the trace is not affected. The trace is not affected. Right, so A and B have the same characteristic polynomial. Okay. Now this is again not difficult to prove. Now if we look at that expression and we get the determinant of that expression, that is going to give me the characteristic polynomial of the matrix A. So if we take, if we multiply that on both sides with, on the left hand side with P's inverse, on the right hand side with P's inverse, and on the left hand side with P, we get, right, so that's going to be lambda multiplied by the identity matrix minus the matrix B. Okay? And so if we look at the determinant of the matrix lambda I minus B, that is going to be the determinant of that expression. And again, the determinant distributes. There we get the determinant of P, okay, multiplied by the determinant, and you will see immediately that the two basically have exactly the same characteristic polynomial. Right? Multiplied by the determinant of P to the power of minus 1. Right, so that is equal to the determinant or the characteristic polynomial of the matrix A. Okay, so again, the characteristic polynomial doesn't change under this operation. Okay, so this property here is that the eigenvalues of A and B are the same. And that follows from property 6. Because both the matrix A and B have the same characteristic polynomial. And therefore the polynomial is going to give the exact same eigenvalues for the matrix A and the matrix B. And then the last property states that if A and B have the same eigenspace dimension, in other words, if lambda is an eigenvalue of A, and then obviously it's going to be an eigenvalue of B as well, then the eigenspace of A corresponding to lambda and the eigenspace of B corresponding to lambda have exactly the same dimension. But to see that, again, it's very similar to the other proof we did for the rank and the nullity. Right, so if you take a basis for the eigenspace of A corresponding to lambda, again, these vectors are linearly independent and they span the eigenspace. We're going to just quickly construct a basis for the eigenspace of B corresponding to lambda. And all we do is we take a vector y such that y lies in the eigenspace of B. Right, so let y bar be in the eigenspace of B corresponding to lambda. So hence we have that property there. So we can replace B with, right, so we can replace B with that matrix. Right, so we can then go and regroup, multiply on the left with P, and then with P there, and basically get this expression here. So therefore, Py is in the eigenspace of A corresponding to lambda. Right, so that implies that we can express Py as a linear combination of the basis vectors. Right, so you can express it there as a linear combination of the basis vectors. Okay. So y is in the span of these vectors, right? So again, the question is, are these vectors linearly independent? And again, we take all our vectors there, and we set up our linear independence equation. We look for scalars k1 up until km. Then again, if you set up that equation there, that's going to imply that, okay, so there we set it up, and then you can multiply straight through by p, and you get then your next expression there, which is this one here. And because those vectors are linearly independent, it simply implies that k1 is equal to k2. They are all 0. So those vectors are linearly independent, okay? And so it forms a basis. Right, so it follows that this set here forms a basis for the eigenspace of B corresponding to lambda, okay? And what is the dimension of the eigenspace of B corresponding to lambda? It is M, right? So the M such vectors. Now if we go back to my dimension of my eigenspace of A corresponding to lambda, you see that there's equality there. So therefore the dimension is the same, and that proves the property. Alright, so that brings us to diagonalization. So we say a square matrix A is said to be diagonalizable if it is similar to some diagonal matrix. In other words, if I can find a matrix, invertible matrix P, such that using that invariant or using that similarity transformation on A, the resulting matrix is a diagonal matrix. And in this case, the matrix P is set to diagonalize A. Now, obviously, it's not always possible to diagonalize a matrix. There are some conditions that need to hold for it to be possible. So in this example here, they ask us to show that this matrix A can be diagonalized, and that in fact the matrix P diagonalizes it. This is easy to see. Just look at P, the inverse of P. You take A and you multiply on the right hand side with P. Then multiplying those two matrices together, we get that matrix there. And then multiply on the left hand side, we get that diagonal matrix. So I mean, it is clear that this matrix is a diagonal matrix there. So definitely that matrix is diagonalizable. We can find an invertible matrix P such that the similarity transformation changes it into a matrix B, and this B is a diagonal matrix. Right, so the next theorem gives us a necessary and sufficient condition for an n by n matrix A to be diagonalizable. Right, so this matrix A is diagonalizable. That is equivalent to saying that A has n linearly independent eigenvectors. Okay, so why are those two statements mathematically equivalent? Well, to prove that, we need to show that if A is diagonalizable, then A will have n linearly independent eigenvectors, And then we have to show that if A is in linearly independent eigenvectors, then that's going to imply that A is diagonalizable. Right, so we first assume that A is diagonalizable. Then we know there exists an invertible matrix P such that P inverse AP is equal to D, where D is a diagonal matrix. Right, so just for argument's sake, let D be that diagonal matrix there, and let P be that invertible matrix. Okay, now since this is true, we have that the eigenvalues of A are these values here. Now why is that? Because remember we said this is a similarity transformation, and we said we talked about invariance under similarity transformations. So in other words, the eigenvalues of the matrix A is going to be the same as the eigenvalues of the matrix P inverse AP. Remember we said that because those two things have the same characteristic polynomial. So therefore the eigenvalues of A are going to be the values on the diagonal. Remember the eigenvalues of D are the diagonal entries. Right, so observe that the matrix A times P is then obviously the matrix P times the diagonal matrix D. Now let's make another observation. If we take A and we multiply A with the first column of P, right, so we multiply it with that column vector, that's going to be the same. So that is going to give us the first column vector of this. The first column of vector of this is going to be the same as it's going to be the same as the first column vector of that product there, right? So therefore that is going to be the same. That's going to be the same as the first column vector of P times D11, all right? And so therefore that implies that the column vector, this column vector here, it's an eigen vector, right? Then if we just, as an example, take the second column there and we multiply that with the matrix A, that's going to give me the first column of the matrix on the right hand side, which is going to be the column vector of P, the first column vector of P, multiplied by the second eigenvalue, right? And that's going to imply that this vector here is going to be it's going to be a eigenvector. Vector. Right, so it's going to be an eigenvector, and you can follow this process through for all the columns. So it follows that every one of the column vectors is an eigenvector, and therefore we've constructed n eigenvectors. Now the question is, are they linearly independent? Now remember, P is an invertible matrix. And an invertible matrix, what is the reduced row echelon form of an invertible matrix? It's the identity matrix. So therefore, the basis for the column space of this matrix is basically going to contain the basis is going to be the n column vectors, right? Remember how we determined the basis for the column space of a matrix? We looked at the reduced row echelon form, and we looked at where the leading ones are, and those leading ones identified the column vectors that are going to form part of the basis. And because there are n leading ones, it means all n of those vectors are going to be a basis, and therefore they have to be linearly independent. Right, so again, as I said, since P is invertible, the vectors, these vectors, they form a basis for the column space of P. So whence they are linearly independent. Okay, so we've got n linearly independent vectors. So now we need to just quickly look at the reverse. Alright, so assume that A has n linearly independent eigenvectors, okay, and let these eigenvectors correspond to these given eigenvalues. Right, so again, just by definition, these vectors all satisfy these eigenvalue equations, right, for every column vector there. And now it's easy, so all you do is you create your similarity transformation matrix by just throwing all the column vectors together. Right, so you take A, and basically you take all these column vectors. So you take that matrix there. Right, there's your second column. Right, there's your last column. Form that matrix. And that is equal to, right, so that you can write that as pretty much this matrix multiplied by this diagonal matrix. Okay, so now we said these column vectors are all linearly independent. Okay, those column vectors are all linearly independent. Now, if this matrix was not invertible, right, its reduced row echelon form would have fewer than n leading ones, right, and that would imply that and that would correspond with fewer than n column vectors that will form a basis for your column space. So that can't happen. So basically, this matrix P that you constructed is definitely invertible. So therefore, you can go and invert you can go and invert this matrix, right? Okay, so we can write it there. Okay, and we can do that. And we can take that matrix, multiply it on the left hand side with the inverse there. So we can go and invert that matrix, and so we can go and diagonalize the matrix A. Right, so those are the two, those two mathematical statements are equivalent. You can diagonalize a matrix if and only if it has n linearly independent eigenvectors. Right, so theorem 2 is quite interesting. It says that if you've got k eigenvectors of a matrix A corresponding to distinct eigenvalues, then that set of vectors is definitely going to be linearly independent. Okay, so whenever you've got a set of vectors that correspond to distinct eigenvalues, that set is always going to be linearly independent. Right, so theorem 5. We'll look at the proof just now because it adds value to our understanding of diagonalization and all of that. If you look at theorem 3, if an n by n matrix A has n distinct eigenvalues, then A is diagonalizable. Right, so why? That follows straight from theorem 2. If you have n distinct eigenvalues, then what you can do is for each one of these distinct eigenvalues, you can go and work out an eigenvector. And by theorem 2, these eigenvectors have to be linearly independent because they're corresponding to n different eigenvalues. And because it has n linearly independent eigenvectors by the previous theorem, by theorem 1, it will immediately imply that my matrix will be diagonalizable. Right, so this example here, they ask us explain why this matrix is definitely going to be diagonalizable by just inspecting it. Okay, first of all, this is an upper triangular matrix. We know that the eigenvalues of an upper triangular matrix is basically the entries on the diagonal. So these are going to be the eigenvalues, 2, 5, and minus 1. Now 2, 5, and minus 1 are distinct. There are 3 of them, different eigenvalues. And by this theorem here, because it has 3 distinct eigenvalues, it will definitely be diagonalizable. Right, so if we look at theorem 2 again, why is it that if you have k eigenvectors and each one of them correspond to distinct eigenvalues, why does it then mean that those vectors must be linearly independent? Right, so let's take k eigenvectors and let's say each one of them correspond to distinct eigenvalues. And now what we claim is this must be a linearly independent set. Right, so let's assume to the contrary that it isn't a linearly independent set. Right, so again, let's assume that this is not linearly independent. So this means that without loss of generality, we can say express V1 as a linear combination of all the other vectors in V2 up until Vk. Okay, so V1 is a linear combination of the vectors up in V2 up until Vk, right? So all I'm going to do is I'm going to choose the largest set of vectors within this set that are linearly independent. Okay, and you'll see later on why I'm making that choice. So we can relabel without getting confused. Let's just call V2, V3 up until Vm, where the index m is less than the index k. Let's just call that the largest set of linearly independent vectors within this set. Now this means that we can write V1 as a linear combination of these vectors here, because we know we can write V1 as a linear combination of all those vectors there, and where appropriate we can replace any vector that is not in this set other than that's not in this set and is also not V1. We can write any such vector as a linear combination of these vectors, and we can just go and replace them there, and therefore we can write V1 essentially as a linear combination of these vectors here. Right, so it follows that we can express V as a linear combination of these vectors here. We can write them as a linear combination of those vectors there. And again, remember what I said, any vector that is not in there, any vector that's not in there, that's also not V1, can be written as a linear combination of these vectors here. right? And therefore, if I write V1 as a linear combination of all those vectors there, the one that wasn't in there I can replace with a linear combination of these vectors here. Okay, so right, so therefore we can express V1 as a linear combination of these vectors. Right, so also recall that each one of these vectors, they correspond to distinct eigenvalues, okay? So now what we're going to do is we're going to we remember V1 is an eigenvector, and V1 responds to the so we just need to remember that V1 corresponds to the eigenvector lambda 1. So if we look at our eigenvector equation, then we get the following. So our eigenvector equation is obviously satisfied because V1 is an eigenvector corresponding to lambda, eigenvector lambda 1. Now we can go and replace V1 with that linear combination we talked about. Right, so let's take that linear combination. And let's plug it in there. And then just using simplification, we can go and simplify that and get. Okay, so simplifying, we just multiplied everything out. We get these terms here, and corresponding to that negative, we get those terms there. Right, now remember, I can go and replace AV2 with lambda 2 V2, right? So we can go and do that. We can go and replace that term there with that term there. And we can go and replace that term there with that term there. So so that whole expression becomes, okay, so that term there stays the same as that. And now I've replaced all those terms there with those terms there, okay? And now we basically group the V2s together, we group the V3s together, and we do that up until we get to Vm. So that expression then becomes, right, so grouping all those terms together, we get that. Now remember, what did we say previously? We said that these vectors are linearly independent, right? So this implies that that needs to be 0, that needs to be 0, and that needs to, all those coefficients need to be 0. Okay, so from that we get that needs to be 0. Okay, that needs to be 0. Okay. Okay, carry on. And that also has to be 0. Okay, so therefore there we've got all those terms equal to 0. Okay. So now the fact that those terms are 0 implies what? Okay, so therefore all these terms have to be 0. Now, what do we know about the eigenvalues? The eigenvalues are all distinct, right? The eigenvalues are all distinct. What does this mean? It means that this term can't be 0, that term can't be 0, right up until the end. None of these terms can be 0. So the only way that those equations hold is pretty much if K2 is equal to K3, is equal to right up until the end, all these terms have to be, they all have to be 0. Okay, but what's the problem with that? If we go back to the original representation, this representation here, what have we just shown? What have we just shown? Right, we have shown there that K2, K3 up until Km, they are all 0. And that is what we've shown. And what is the problem with that? The problem with that is that because these terms are 0, okay, what is the problem with that? It's going to mean that V1 is going to be 0. V1 is going to be 0. And why is that a contradiction? What's the problem with that? Remember, eigenvectors are non-zero vectors, right? Eigenvectors are non-zero vectors. So that's going to imply that V1 is 0, which is a contradiction. And therefore, that's going to force my vectors that correspond to distinct eigenvectors to be linearly independent. Right, so that brings us to Theorem 4. That's just a combination of everything we've done up until now, Theorem 1 up until 3. So this says that linearly independent sets from different eigenspaces forms a linearly independent set when combined under unions. So all they're saying there is that if you take the if you go and work out the eigenvectors out, all the eigenvectors for each one of the distinct eigenvalues, and for each eigenvalue you take a vector, you take a group of linearly independent vectors, right? Then throwing all those vectors together for each eigenvalue, the linearly independent sets, that forms a new set of vectors that's going to be linearly independent. Right, so let's just quickly visualize this. So again, you have your indistinct eigenvalues, and for each one of those distinct eigenvalues, you go and work out a set of linearly independent vectors, and we call these it set 1. Set 1 is a set of linearly independent vectors that correspond to lambda 1. Set 2 is a set of linearly independent vectors that correspond to lambda 2, and up until the end, lambda n corresponds to this linear independent set of vectors there. Now, I mean, obviously, if you throw them together, it's still going to be a linearly independent set, because each one of the sets, blue sets, the vectors in that blue set are linearly independent amongst themselves. And then by theorem 2, which is this theorem here, remember we said eigenvectors that correspond to different eigenvalues, they are always linearly independent. So the fact that each one of the blue sets, the vectors in each blue set are linearly independent amongst themselves, and because if you throw them all together again, that's still going to be a linearly independent set by theorem 2, because all these vectors here, all of them here, they only correspond to their unique linearly eigenvalue. So they are all going to be linearly independent still if you throw that all